have a look at scientific notation and rounding. Now there's, in various fields of science, people tend to work with very large numbers. So you can think about this in terms of astronomy, the distance between us and a particular star. And if we were to measure that in kilometers, as opposed to light years, or even worse, imagine measuring it in meters, you're dealing with this massive, massive number of millions, billions, trillions. It's not a particularly convenient to have to continually refer to this huge number, 325, with, 18 zeros attached. I'm not even sure how to say that number. Similarly, there are other people in fields of science that work with very, very small numbers. So physicists might be talking about the diameter of an atom, or biologists might be talking about the size of a cell, and it's not very convenient to continually refer to, say, the length of a light wave as being 0 point, and then we've got 13 zeros, 168. To continually refer to as that would be very tedious. And so this is where the idea of scientific notation comes about. It allows us to write very large and very small numbers in quite a simple form. And this form looks like A times 10 to the power of K. Now this number A is some number between 1 and 10. More specifically, A is greater than or equal to 1, but it must be less than 10. This guarantees then that A is going to have a single digit before the decimal place. For example, if you took something lower than 1, you'd have 0 point blah blah blah. No, we have to have at least 1. And yet we don't want to have 10 point something. That's why A must be explicitly less than 10. So think of this number in front, A, as being anything between 1 and, 9.99 maybe. And then we're multiplying that number by this power of 10. And K is an integer. So if K is let's suppose that we're dealing with a very, very big number, then K will be a positive integer. But if our number is very, very small, K will be a negative integer. And K kind of represents the number of places that we are going to have to move the decimal point as we convert between normal notation, or standard form, and scientific notation. So let's do some examples, and I think you'll get the idea. When I'm looking at this huge number, because it's a very big number, I know that my power of 10 is going to be a positive exponent. And that exponent represents the number of places that we'll have to move the decimal. So right now the decimal is here at the end, and we want to move it to right here, because this 9 is the first non-zero number that we find. That's how you convert into scientific notation. You seek the first non-zero number as you look at the number from left to right. So now we want to move it to here, so let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We've moved it 15 places. And we use a positive 15 because this is a very big number. And so now we'll rewrite this part, 9.4488. We no longer need to include all of these zeros because when they come after a decimal point at the end of a decimal, they don't change the value at all. So 9.4488. And then if we multiply it by 10 to the 15, that would of course account for the moving of the decimal place 15 times over, 15 places, in order to change it back into standard form. Let's do the next example. Now we have a really small number, and so we know that we're going to be multiplying by 10 to a negative power. Let's see what that negative power is. I'm going to look at my number from left to right and stop when I find my first non-zero number. My first non-zero digit is right here, the 5. And so right after that 5 is going to be the location of my decimal point. Remember, we want this number before the decimal point in scientific notation to be between 1 and 10. Here it was a 9, great. Here it's a 5. Great. In fact, more specifically, it was 9.4488. And in this case, it's going to be 5.304. And how many decimal places do we have to move it? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we are raising it to the power of negative, oops, what have I done? We're raising it to the power of negative 14. There we go. Next example. We have to now go the opposite way. Let's write this number, which has been given in scientific notation. You'll notice that it's a number between 1 and 10, being multiplied by 10 to the power of an integer. And you'll notice that this is a positive integer. So we expect our final answer to be very big, right? And that means that we're going to be moving the decimal to the right by 9 places. So here's our 6.1. This was the old place of the decimal. Let's now move it over 9 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, creating a very big number. And I'll fill in zeros everywhere where I don't have anything. So let's count again. 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. And now I've moved it over 9 places. It might have been nice, I suppose, to plan ahead a little bit and create little spaces where there's each groupings of 3. So we can see, for example, this number is 6,100,000,000, and there's no thousands or ones. And let's take this number, 2.02 times 10 to the negative 3. This is a very small number. In order to make it small, we're going to need to move the decimal to the left. And of course, we're going to have to move it 3 places. 1, 2, 3. And so if the new location of the decimal is there, we've now got 0 point, and let's see, we have to fill in 2 zeros here as we move the decimal over, and we created a 0 point. We created 2 additional zeros before our 202. Let's just confirm that we did indeed move the decimal over 3 places. It began at 2.02, 1, 2, 3. There we go. And again, it might have been nice if I had created this grouping where I'd had 0 point, here a group of 3, 0, 0, 2. And now here we don't have a full group of 3. But anyway, little spaces where I've put these notches makes your number a lot easier to read. It's a lot clearer how large or how small your number actually is. On a calculator, very large and very small numbers are expressed in scientific notation because the answers are too big or too small to fit on the display. Imagine your calculator doesn't have enough digits to give this full number. Let's just demonstrate this. So I'll type in 94488. And now we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Did I get them all? 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops, 2 more. 10, 11. I hit enter, and look what it's done. It's rewritten that big number in scientific notation. Now, the calculator has a slightly different notation for scientific notation. They use this capital E instead of when they describe the power of 10. So instead of writing, for example, in this one, 7.82 times 10 to the 14, they will replace that times 10 with a capital E. And that's what's happened here. We've got 9.4488 times 10 to the power of 15, just like we knew it was. So that's how you interpret the capital E on the calculator. So let's just practice this. We'll write the calculator display number, this one, in normal scientific notation. We change that capital E into a times 10 to the power of, and then we have a 7. I don't need to write the 07. The calculator will always give 2 digits in the, for the power of 10. 10 to the power of, in this case, 15, or 10 to the power of 07. But when we're writing it in normal scientific notation, there's no point including the 0. Next one, write the calculated display number 6.83, capital E, negative 52. So we just need, again, to replace that capital E with a 10 to the power of, and now I have negative 52, an extremely small number if you move the decimal over 52 places. Alright, now we've got a calculated notation that we have to write into standard form. So we first interpret this in regular scientific notation as 1.97 times 10 to the power of negative 3. It's a negative exponent, which means that we're going to be aiming for a small number where we have to move the decimal over 3 places. 1, 2, 3. There's the new spot of the decimal. And of course we have a 0 before that. We've got to fill in 2 zeros into those 2 spaces. So we end up with 0.00197. And let's just verify we did end up moving the decimal 3 places. It was after the 1. 1, 2, 3. Great. Write the calculated display number 9.2 E11. So let's interpret this. 9.2 times 10 to the power of 11. 10 to the power of a positive integer. That creates a very large result. And so we're going to look for a large number. We have to move the decimal over to the right. We're going to move it over 11 places. Let's start with my 9. And remember my decimal was here, right after the 9. So here we go. Let's move it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Boy, I'm out of room. 10, 11 places. And I have to fill in zeros in all of those spots. 1, 2, 3, 4, 5, 6, 7, 8, 9. I have to fill in 0 into 10 spots. So let me just write this a little neater. And so I have a 9, a 2, and I think we concluded there were 10 zeros. So 9, 2, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you see what I mean by my grouping? I've created little spaces after every group of 3. And that way we can see these are the ones, these are the thousands, these are the millions, these are the billions. So we have 920 billion, and no millions, no thousands, or ones. Now then, suppose that you did a traffic survey and discovered that you had 1,852 cars. They're carrying 4,376 people. I mean, we could do the division here, 4,376 divided by 1,852 to find out the average number of people being carried per car. But can you imagine if you gave somebody the answer? Oh, okay, how many people per car? 2.362850972. That is kind of a little bit more descriptive than you need to be. It's too precise. I think it's going to be appropriate to just say, look, around 2.4. Instead of wasting our time giving all of this precision that the person who posed the question to you probably wasn't looking for. So this means that we need to shorten or round off some numbers which have got more figures in them than we require. There's 2 ways to do rounding. We usually round off to a certain number of decimal places, or we round to a certain number of significant figures. And should just add that if the number is given to you in scientific notation, you should probably convert it into standard form first. Alright, these are standard form, just regular numbers, as opposed to scientific notation. It's going to be a lot easier, I think, to round correctly if you've got it in standard form.